Hello and welcome to this lecture. We started the study of eigenvalues, eigenvectors, we motivated it a lot with powers of a matrix, isn't it? So, how do you deal with powers of a matrix? So, let me show you how you can do that once you have diagonalizability. So, let us say you have A being a matrix here, or whether you have diagonalizability or not, you can use it. So, let us do that. Okay. So, you have a matrix A here, maybe A11 are real of course real numbers, and eigenvalues may be evaluated to lambda 1, lambda 2. You can have two situations, right? It could be diagonalizable, in which case there exists an invertible S such that A is S lambda 1 0 0 lambda 2. The columns of S are basically the eigenvectors corresponding to lambda 1 and lambda 2, right? We know how to do this. Okay. So, now what happens when you have A equals S diagonal S inverse? What is A squared? S times, I am writing A here, right? This is A, right? A times A, this is A again, right? Now, notice what happens here, you have S inverse S. What is S inverse S? It is identity. Once this goes away, this cancels, it goes away. You have lambda 1 0 0 lambda 2 multiplying lambda 1 0 0 lambda 2. So, that simply becomes lambda 1 squared 0 0 lambda 2 squared, and you have the S and S inverse hanging along, just one power there. So, notice how this is working out wonderfully in the matrix algebra for powers, right. So, in terms of operators, this is very silly, I mean, it's just, you're just saying t itself has eigenvalue lambda 1, lambda 2. So, you can do t squared very differently, the operators, it will work very differently. But for matrices, notice how it works. This matrix here, which was non-zero, I was able to diagonalize, write it like this. And then A squared simply becomes the square of the diagonal values alone, and then S and S inverse sitting there because of this cancellation. So, you can repeat this now. I can do A cube, A power 4, etc. And you can quickly see for any A power n, any matrix power, your diagonal values are going to be raised to that power, lambda 1 power n, 0, 0, lambda 2 power n, but you still have to stick the S and S inverse on both sides. Okay, so this is how you deal with matrix powers when in the diagonalizable case. If A is diagonalizable, A power n is just S, the matrix diagonal powers S inverse. Okay, so very, very simple way to characterize the powers of a matrix, right? So, all the different types you got. Unfortunately, you may also get the non-diagonalizable case. In the 2 by 2 case, this is not too hard. In the non-diagonalizable case, what happens? Lambda 1 equals lambda 2 equals lambda, and there exists an invertible S such that A is S lambda alpha 0 lambda S inverse. Okay, we know that this is true, right? Upper triangular is possible for any operator. Okay, so you can do lambda 0 alpha lambda. This alpha will not be 0 in this case, in the non-diagonalizable case. But this is okay, I can use my same trick that I did here with this form, right? I have reasonably simple form here. So, I can do A power n, I will get this as S lambda alpha 0 lambda power n S inverse. So, how do you do this power? It turns out the answer is this, okay. I am not going into great detail here, it turns out the answer is lambda power n, n alpha lambda power n minus 1, 0 lambda power n. You can prove this by induction. How do you prove this by induction? If you take this and multiply by this, what do you get? You will get lambda power n plus 1, and then you will get n lambda and n alpha lambda power n plus alpha lambda power n, which is n plus 1 into alpha lambda power n. Then the 0 will be 0. Okay, so you can see that will be 0, and then the final value will be lambda power n plus 1. So, by induction, you can prove this very, very easily. I will leave that as an exercise. You can post it in the forum if you like. So, this will be an easy thing to show. So, what we have found is that the power of A power n can be explicitly calculated using this eigenvalue, eigenvector idea. Okay, so in one case you have upper triangular case, it's okay, but you can still find it. In the other case, you have the diagonal case, which is very, very easy. Okay, so this we are going to use in all our examples. You remember the examples we started out, which you couldn't understand where it was coming from. We are going to use these ideas and solve these powers of the matrix. First thing is, what are eigenvalues, eigenvectors? It's the first thing, we already done it before. It's 0.5, 1 minus 1 and 1.5, 1, 1, right. So, these are eigenvalues, eigenvectors. So, this is a diagonalizable case. Okay, so you can see that A will become 0.5, 1.5, 0, 0, and then this is the eigenvector basis. Okay, 1 minus 1, 1, 1, and this is the inverse of this matrix. Okay, right. The determinant will end up being 2, and then you have to do this, the values will be written. So, you can see that this ends up being the inverse of this matrix. Okay, you can check that. You can check that in multiple ways. So, these two are inverses. Okay. So, A is this. a power n will then become, these two will be exactly the same. Here you will have 0.5 per n, 1.5 per n. So now you can try and simplify. When you try and simplify, this ends up being this. Okay. So 0.5, 1.5 per n plus 0.5 per n, this is what you get. Okay. Now notice what happens here. If you remember, if you go back and look at our example, this a power n ended up, all four values tended to the same value when n increased. Why is that true? You can see, as if you tend to limit as n tending to infinity for large values of n, this 0.5 per n will become too small. Only the 1.5 per n will dominate. So this will tend to 0.5, 1.5 per n, 1.5 per n, 1.5 per n, 1.5 per n as n tends to infinity. So this tends to blow up. Okay, so notice how we are able to precisely nail down. So this is actually an exact expression, by the way. For any n, this is an exact expression. For large n, we are able to approximate to this kind of value. Okay, so our first example is solved. Let us look at the second example. So in fact, there was this other example where we multiplied this by 0.5. If you multiply by 0.5, all you are going to get is 0.5 power n here, and that will go in and that will change these values to something else. Okay. Okay. This is example 2, okay, which was 1, 1 minus 1, 1. So in this case, what happens is your eigenvalues eigenvector pair ends up being complex. So the calculation will be complex numbers calculation, a little bit more intricate, but it can be done. So you get 1 plus I minus 1, and 1 minus I eigenvalue, eigenvector is I comma 1. Okay. So what happens now? A can be written as I minus 1 I1, right? That is the basis vector, basis matrix, times the diagonal matrix times the inverse of this guy. So inverse of this guy, again you can use the same sort of formula, you will get the inverse. Okay, so this is the inverse. Okay, I mean, if you do not believe me, you can multiply and check this. This is the inverse. Okay, so if you do a power n, what will happen? These two remain the same. This diagonal alone goes to the power n because these two are inverses of each other. This happens. Okay. So now how do I simplify this? In the previous case, I was able to simplify this. How do I simplify this? It turns out you have to do the rectangular to polar coordinate change. Okay. So this 1 plus I is root 2 e power I pi by 4. 1 minus I is root 2 e power minus I pi by 4. So you apply that and then you multiply this out and simplify. I'm not showing you all the simplification. I'll leave this as an exercise. Take a piece of pen and paper and go through and make sure that you get this right. Okay. So this ends up being this. So this is an exact expression. Okay. You can simplify this further because at the end of the day, A is a real matrix. So A power n should be a real matrix. We have all these i's floating around here. So they should all cancel and become, you can write it in terms of cosines. So if you do that simplification, this is maybe easy to see. Okay. E power x plus e power ix plus e power minus ix is 2 cos x, right? So that's what I've used here. Here I've used the sine formula. Basically, e power I theta is cos theta plus I sin theta. So you use that. So you get this. So you see that this is root 2 power n times this cosine n pi by 4 sin n pi by 4 type things matrix. So it's the same as root 2 power n, a periodic matrix. No, this has a period. Every 8 n equals 8, it starts repeating. This is a periodicity 8. We saw that periodic property when we raised this 1, 1, minus 1, 1 to the power. Okay, so here is the power of eigenvalues, eigenvectors in figuring out the powers of a matrix. The last example I'm going to take is slightly different from the example we had in the earlier. It's an off diagonal. It's one of those deficient cases. 2, 0, 1, 2. So here I have only one eigenvector. No, I don't have the other guy. So 2 is eigenvalue 2 and eigenvector is 0, 1. That's the only eigenvector. So I have to make a basis. Let me make a basis. V1 is 0, 1, V2 is 1, 0. Okay, so this is the basis. And I have my S being 1s. Notice how we have to be careful here. S is the first column is 0, 1, second column is 1, 0. It's sort of like, it's not identity types. So S inverse is also the same. Okay, you do the inverse, you'll get the same guy here. And if you do AV1, A times V1, you're going to get 2V1, and A times V2 is going to be V1 plus 2V2. So the matrix, okay, the matrix A can be written as S times the matrix here. The matrix here is 2, 0 and then 1, 2. I hope you see that, 2, 0 and 1, 2, okay, and then 0, 1, 1, 0. So this is sort of like a transposition here. If you see what is going on, that's what happens here. But this is, we just went through the process and got it, right? We found the diagonal, the upper triangular matrix here. So when you do a power n, you use your formula. We have a formula for this, lambda, lambda, alpha here, 0 here. You use that formula, you get this. But then there is the 0, 1, 1, 0 to worry about. You will get this guy. Okay, so you get 2 power n 0, n 2 power n minus 1, 2 power n. So this is a way to figure out matrix power. So whatever matrix you have, 2 by 2 matrix, you know how to do the power. Okay, so that's the answer that you get with eigenvalues and eigenvectors. Thank you very much.